Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. There is a certain stillness that settles over the mind when the world grows quiet, a softness that spreads gently through the spaces between thoughts, where curiosity begins to feel less like a sharp, active search, and more like a slow drift into something deep and luminous. And in that quiet, a question begins to form. Not loudly, not urgently, but like a small ripple moving across a vast, calm lake. A question about consciousness and the strange, shimmering world revealed by quantum mechanics. A question about how these two mysteries might touch one another, not in a sensational way, but in a subtle, scientific, almost dreamlike way. Before anything else, the mind softens into the mystery of consciousness itself, this strange interior light that knows it is aware, this presence that experiences each moment, that feels and remembers and wonders. Consciousness is at once the most immediate thing we know, and the most difficult thing to explain. We can point to neurons, chemistry, signals moving in intricate patterns. We can describe behavior, map regions of the brain, predict responses. But the feeling of being aware, the experience of the world from the inside, the simple presence of I am, remains unquantified, untouched by instruments, present, yet elusive, like the faint glow of a candle seen from far across a dark room, clear enough to notice, but impossible to grasp. And then, there is the strangeness of quantum mechanics, the physics of the very small, where particles don't behave like solid objects, where existence becomes a haze, a field of possibilities, where position, energy, and even identity seem to drift in soft layers of probability, where certainty dissolves into something fluid, where reality feels less like a rigid structure and more like a shimmering fabric still deciding what it will become. Quantum mechanics is not chaotic, but it is unconventional. It is delicate, mathematically precise, yet profoundly unintuitive. It shows us a world where the boundaries of is and could be are thin, almost permeable, a world in which the smallest components of nature seem to hover between potential outcomes, awaiting something, awaiting interaction, awaiting the moment when possibility narrows into fact. And so a question gently rises. What is the relationship between consciousness and this quiet unfolding of quantum possibilities? Not as a claim, not as an assumption, but as a curiosity. Because in the equations of quantum physics, in the subtle mathematics that describe wavefunctions and measurement, there is a role for the observer. Not necessarily the human mind, but the act of observing, the act of measuring, the act of interacting with a system that is still in its state of possibility. And this simple fact, that the universe behaves differently once information is extracted from it, invites contemplation. It invites a soft exploration of the boundaries between the observer and the observed, between awareness and the physical world, between consciousness and the unfolding of reality. So the question remains, a question we will drift into tonight with calm, with clarity, with scientific honesty, and with a touch of poetic quiet. Does consciousness create reality? Not in the dramatic sense, not in the mythic sense, but in the subtle way suggested by the mathematics of quantum theory. Could the mind, the observer, the one who knows they are aware, play a part in the transition from possibility to actuality? Could the presence of consciousness be linked, even gently, to the way information becomes fact? Or is consciousness merely a witness, a bystander in a universe that collapses wave functions without needing awareness at all? These questions have echoed through the deepest discussions of physics, not because the answers are clear, but because the mystery remains open, not because science fails, but because the universe is richer and more subtle than our everyday frameworks allow. And so tonight we step into this mystery, Not with tension, not with expectation, but with a slow, quiet curiosity, a willingness to let the mind wander carefully through the intricate world of quantum possibility, a willingness to let go of our everyday assumptions, just for a moment, a willingness to drift, to allow the questions to unfold on their own, to let the complexity of the universe wash gently over our awareness until thought becomes soft and understanding becomes spacious. We begin by settling into stillness. The breath slows, thoughts soften, awareness becomes wide, open, receptive, as if the mind itself is entering a kind of superposition, holding multiple ideas at once without needing to choose between them, holding mystery without needing resolution. Just to sit with the beauty of not knowing, the beauty of inquiry, the beauty of a universe that reveals itself only gradually, only when approached with patience, with humility, with wonder. And in this softness a direction emerges, to explore the nature of consciousness, to explore the behavior of the quantum world, and to explore the subtle, almost hidden ways in which the two might intersect, not with conclusions, but with clarity, not with assertions, but with openness, not with certainty, but with scientific calm. The night becomes a quiet canvas, the universe becomes a field of gentle questions, and consciousness, the one experiencing this moment, becomes the witness to the unfolding mystery, a mystery that invites us to look not outward and not inward, but into the space between, where physics meets awareness, and awareness meets reality, and reality rests in possibility. And so, with the mind soft and the breath easy, we drift onward, into the deeper layers of this quiet inquiry, where the fabric of the universe begins to shimmer, and where the smallest motions of reality begin to whisper their secrets, letting us move gently into what comes next. In the softness of this moment, with the mind loosened and thought drifting like gentle dust in a beam of light, we begin to move toward the strange interior of the quantum world, a place so quiet, so delicate, that even language feels heavy compared to the subtlety within it, a place where reality seems to shimmer between what it is and what it could be, a place where the ordinary rules of the everyday world no longer apply. And yet, everything in the universe is built from this place, every atom, every photon, every molecule, every cell, every star. The smallness is not trivial, it is foundational, it is the quiet fabric beneath the familiar, the part of reality we rarely see directly, but that shapes everything we call real. To step gently into this deeper layer, we begin with the concept of a quantum state, not a location, not a trajectory, not a solid unchanging property, but a soft field of all the possibilities a system can take. A quantum state is not a single answer, but a space of answers, a mathematical structure that allows the universe to hold many potentials at once. A quantum particle is not committed to a single future. It exists inside a cloud of potential behaviors, a little bit here, a little bit there, a little bit drifting through what we would call mutually exclusive realities, all layered together in a quiet harmony. The quantum state is the universe's openness, its flexibility, its willingness to hold multiple stories before deciding on one. This leads softly into the idea of superposition, a word that once sounded exotic, but now feels like a calm description of how possibility behaves before it crystallizes. Superposition does not mean confusion. It does not mean indecision. It means coexistence. The coexistence of many allowed states, layered, entangled, blended. A particle is not choosing between them. It simply is all of them, in the only way nature allows at scales this small. An electron is not walking along a single path. It is exploring a multitude of paths simultaneously. A photon does not slip through one slit. It exists through both, interfering with itself, as if it is aware of every possible route its wave function can take. Superposition is the quantum world in its most open form, a soft unfolding of overlapping futures, a gentle dance of what may be, but the openness is not chaotic. It is structured, beautifully structured, expressed through the mathematics of probability waves. These are not waves of matter, not ripples of physical substance. They are waves of likelihood, shapes that express how strongly the universe leans toward different outcomes. At a peak of the wave, the potential is high. In a valley, it is faint, and these waves do not remain isolated. They merge, they overlap, they interfere. A crest can strengthen another crest. A trough can cancel a crest, and entire patterns emerge, patterns that guide how the world behaves before a measurement is made, patterns that reveal the hidden order beneath the surface, a quiet geometry of potential outcomes. Interference is the whisper of probability, the soft structure of the quantum world's preferences. Most of what we see in everyday life contradicts this behavior. Our intuition is built from large things, stones, chairs, trees, the slow rhythm of the human body. We expect objects to occupy one position at a time. We expect events to unfold in a single sequence. We expect certainty to be the natural state of the world. But at the quantum scale, certainty is the exception. Possibility is the rule. And so classical intuition fails, not because physics is broken, but because our senses were never meant to perceive events so small. The brain evolved to keep track of stable objects, not probability amplitudes, to predict the behavior of predators, not interference fringes, to follow the flight of an arrow, not the wave function of an electron. Quantum mechanics is not strange. It is precise. It is we who are too large to see it clearly, too bound to the certainty of macroscopic experience, too accustomed to the solidity of everyday matter. But when we let that intuition soften, when we let go of the need for classical certainty, a new kind of intuition appears, an intuition built from probability and superposition and delicate structure, a quieter intuition, born from the mathematics that has never once failed to describe the smallest scales of nature. And this leads naturally, yet delicately, to one of the most subtle distinctions in physics, the difference between measurement and ordinary observation. In daily language, to observe is to look. To measure is to record. But in quantum theory, the meaning is different. A measurement is not about human awareness. It is not about noticing. It is the physical interaction between a quantum system and something capable of storing information, a photon scattering off an atom, a detector absorbing light, an electron bumping into a particle of air. These interactions extract information. They force the quantum state to narrow. They turn possibility into actuality, and none of this requires a mind. It requires an exchange, an entanglement, a transfer from the openness of many states into the specificity of one. Human observation is something different. It is awareness, it is consciousness, it is the subjective experience of receiving information. Quantum mechanics does not require this. It only requires a physical process that leaves a trace, a record, a correlation, something that encodes the outcome. This distinction is one of the keys to understanding why quantum mechanics has stirred decades of philosophical discussion. It invites us to reflect on the boundaries between the physical world, the informational world, and the conscious world, boundaries that may be sharp, or may be soft, or may be illusions arising from our limited perspective. And then, in the quiet spaces between these ideas, another truth emerges. The structure of the quantum world is almost eerily gentle. It is not a world of tiny spheres colliding, not a world of miniature billiard balls knocking into one another. It is a world of clouds, of fields, of waves, a world where an electron is not in a single place but spread like a mist around a nucleus, a world where paths are not chosen but superposed, a world where the laws of motion are expressed not through fixed trajectories but through probabilities. This strange softness is not imprecision, it is depth, it is subtlety, it is the quiet architecture of the smallest layers of nature, a structure built from mathematics, from wave functions, from interference patterns, a structure that feels almost dreamlike and yet is more accurate than any classical picture we have ever created. All of this leads us to one of the most profound realizations in quantum physics. Particles do not have definite properties until certain interactions occur. A particle does not have a single position waiting to be discovered. Its position is created through measurement. Its momentum is not hidden, it is undefined. Its energy is not waiting in secret. It emerges from the act of extracting information. Reality is not a set of fixed facts. It is a field of potential facts, a field that becomes definite only when something forces the universe to specify. This is not metaphor. It is the mathematical core of quantum theory. The properties of quantum systems are not definite until they must be, until the moment their potential narrows, until the soft blur becomes a single point, until something touches them. All the ideas in this part have now unfolded, each of them forming the quiet foundation needed to understand the deeper mysteries ahead. And so, with calm, with softness, with a mind shaped gently by possibility. We drift onward, letting the next layer of the quantum world begin to reveal itself. In the quiet depths of the quantum world, there is a moment so subtle that it cannot be seen, cannot be touched, cannot be watched in any ordinary way. A moment when the soft haze of possibility folds inward, when the shimmering cloud of what a particle could be narrows into a single outcome, when the universe in its most delicate whisper decides. We call this wavefunction collapse. But collapse is only a word. A human attempt to describe something that does not shake the world with force or finality. It is not an explosion, not a shutter slamming, not a sudden violent snap from one state to another. It is quiet. It is subtle. It is closer to an update, a gentle narrowing, a shift from openness into a single, revealed fact. And to understand this moment, we must return to what the wave function truly is. Not a wave of matter, not a wave in space, but a wave of information. A map of probabilities, a soft mathematical glow describing every place a particle might appear, every energy it might hold, every path it might take. The wave function is the universe's way of speaking in maybes. It is the language of potential, a language that only becomes a statement when something asks a question, when something interacts, when something touches the system and forces the universe to reveal a single answer hidden among countless possibilities. That moment of revelation is collapse. If you listen closely to the rhythm of this idea, you begin to sense something profound. Collapse is not about destruction, it is about clarification. It is the moment when uncertainty shrinks into a fact, when somewhere becomes here, when perhaps becomes this. The wave does not burst, it simply changes shape. It is replaced by a narrower description, one that reflects the new information gained from the interaction. Collapse is the universe updating its story. But does this update happen physically? Does the wave truly change as a real process in nature? Or does collapse happen only in our description, only in the shift of what we know? Here, physics drifts into philosophy, because no experiment has ever caught the wave function in mid-collapse. No device has ever recorded the moment probability narrows into certainty. We only see what comes before and what comes after. The transition itself is veiled. Some physicists believe collapse is not physical at all. They say the wave function is a tool, a bookkeeping device, a way for us to track information about a system we cannot fully see. In that view, collapse is simply the moment when our knowledge changes, when the book is updated, when the information shifts. But others believe the wave is real, that it stretches through space, guiding possibilities, and then folds inward when the system is touched. Two visions of reality, one where collapse happens in the universe, and one where collapse happens in the mind of the observer, and the truth still rests in the shadows. To drift deeper into this mystery, we must gently meet one of the most important ideas in modern quantum theory: decoherence, a soft word for a subtle process. Decoherence is what happens when a quantum system is not isolated, when it becomes entangled with its surroundings, when every vibration, every photon, every tiny interaction in the environment carries away information about the system's state. And as information leaks out, as the system becomes woven into the fabric of the environment, its delicate quantum coherence begins to fade. The superposition no longer behaves like a single unified wave. It spreads its correlations into the world around it, into dust particles, into air molecules, into scattered light. The environment acts like a vast observer, not conscious, not aware, but interacting in a way that progressively narrows the possibilities. Decoherence does not choose an outcome, but it destroys the interference between possible outcomes. It gently erases the quantum strangeness, leaving behind a set of classical-like states that no longer overlap in the soft, ghost-like way they once did. And it happens constantly, every moment, to every unprotected quantum system immersed in the world. In this view, collapse is not a single event, but a smooth unraveling of quantum possibilities into the tangled web of the environment, a quiet blending of system and world, a dissolving. But the history of collapse did not begin with decoherence. Long before our modern understanding took shape, physicists were wrestling with a deeper question. What does it mean to measure something? Is measurement something an observer does, or something the world does on its own? In the early days of quantum theory, measurement was mysterious. It was a special act, a kind of dividing line between the quantum world and the classical world, between the uncertain and the definite, between the wave and the particle. Some early thinkers imagined that consciousness itself was required, not awareness in a mystical sense, but simply the idea that a mind must register the result, that collapse does not complete until the outcome enters experience. This idea was never a consensus, but it echoed through the history of physics, leaving behind a trail of questions. Not because physicists believed consciousness had magic powers, but because nobody could define what a measurement truly is. Where does it begin? Where does it end? What counts as an observer? A Geiger counter? A camera? A grain of dust? A photon? Or only a mind? The line was never clear, and for decades the ambiguity remained, giving rise to entire families of interpretations, some that emphasize information, some that emphasize the environment, some that emphasize mathematics, and some that quietly leave the door open for consciousness to play a role, not as a proven necessity, but as one possibility among many. A possibility that lingers because the boundary between quantum and classical remains blurry, and collapse remains unseen. This brings us to a final question woven through the heart of measurement theory. When does a quantum system stop being a wave and become a fact? What counts as the moment the universe chooses? Is it when a detector clicks? When photons scatter? When molecules vibrate? When neurons fire? When awareness arises? Physicists debated this not out of speculation but out of necessity, because the theory itself does not specify where the line falls. The equations describe the flow of probabilities, but not the moment the probabilities fold into certainty. This gap is where interpretations bloom. Some eliminate collapse entirely, some redefine measurement. Some replace uncertainty with hidden variables, and others allow the possibility that the observer may be more deeply woven into the story of reality than we once imagined. Not as a magical force, but as one possible layer in a universe that still refuses to reveal its full design. Collapse remains one of the quietest mysteries in all of physics, a moment we cannot see, but always infer, a moment that shapes every experiment, every observation, every path a quantum system might take, a moment where the universe softly chooses. There is a strange stillness hidden inside the quantum world, a stillness that should not exist, and yet does. A stillness that emerges not from silence and not from isolation, but from watching, from observing, from touching a system again and again, so gently, so repeatedly, that its natural motion is held in place, as if the universe itself hesitates beneath the weight of steady attention. This quiet phenomenon is known as the quantum Zeno effect. And to drift into it is to drift into a paradox where doing more leads to less, where interruption creates stillness, and where the simple act of checking can reshape the very unfolding of reality. The story begins in the soft, delicate motion of a quantum system. At the smallest scales, particles evolve in time according to gentle mathematical curves. Their wave functions spread, shift, interfere, drift into new configurations. Like ripples expanding outward from a single drop in calm water, this evolution is natural, quiet, continuous. Unless something intervenes, unless the system is measured, because measurement does not allow gentle evolution. Measurement sets boundaries. Measurement asks the system to choose. Measurement collapses the wave function into a new, definite state, and from that state, the wave function begins evolving again, spreading, gradually, slowly, until the next measurement arrives, and the next, and the next. It is here that the strangeness begins. If a system is left alone, it evolves freely. But if it is measured over and over in rapid succession, the collapse interrupts the evolution. The wave function is forced to restart again and again, never gaining enough time to drift into a new configuration, never gaining enough distance from where it began. The system becomes trapped near its initial state, frozen, not by cold, not by confinement, but by attention, by being watched, watched relentlessly, watched continuously, watched so often that evolution cannot unfold. The idea first appeared in the 1970s, a time when physicists were exploring the boundaries of quantum measurement. The researchers noticed something peculiar. A quantum system that would normally change state after a certain amount of time could be prevented from changing if they checked on it frequently enough. Like a candle flame that flickers when left alone, but steadies when observed. not because the watcher stops the flame, but because the act of checking breaks the flow of its natural oscillations. The analogy is not perfect, but it captures the feeling, the subtle sense that watching gently binds the system to what it was, holding it in a state of near stillness. To understand why this happens, we drift deeper into the mathematics beneath the poetry, but we keep the explanation soft, sleep-friendly, a quiet unveiling rather than a sharp one. Imagine a quantum system in some initial state. Left alone, its wave function slowly spreads into new shapes. Its probability distribution moves outward. The chances of finding it in different states begin to rise. If we measure the system after some time, there is a chance the system will be found in a different state than it began. That chance increases as the wave function spreads. But if we measure the system very quickly, before the wave function has time to spread, the probability of finding it anywhere else remains extremely small. Because the wave function has not moved, it has not evolved, the collapse returns the system to its original state, and from that moment, the spreading must restart. But if the next measurement comes too soon, the spreading is interrupted again. Collapse, restart, over and over, until the system is effectively held in place, motionless, not by force, but by repeated inquiry, by repeated demands for certainty. The universe cannot change under the pressure of constant questioning. This effect was eventually confirmed in laboratory experiments. Atoms and trapped ions became the testing ground. Researchers prepared systems that would normally transition from one state to another. Then they measured them rapidly, faster than the natural timescale of the transition, and the transition slowed, then halted, as if the system were pinned to its starting point. Held gently by the hands of incessant observation, the results were unmistakable. The effect was real. Watching changes the behavior of quantum systems, but not because consciousness is exerting force, not because the mind is bending reality, but because measurement creates collapse, and repeated collapse interrupts evolution, like stopping a wave before it crests, over and over, until the water never rises. Still, it is easy to see why people found the effect mysterious. A system watched constantly refuses to change, refuses to decay, refuses to move forward, the universe hesitating under attention. The parallel to consciousness was too tempting, too poetic, too intriguing, and so popular interpretations arose. Ideas that suggested a conscious observer could freeze motion, ideas that claimed reality responds to awareness, ideas that hinted the universe depends on being seen, but the physics remains quieter, simpler, and more subtle. It is not awareness that freezes the system. It is measurement. Measurement in the physical sense. Any interaction that extracts information, a detector firing, a photon scattering, an atom absorbing energy. The universe does not ask whether a mind is watching, only whether an interaction occurred, only whether a record was made. And yet, the poetry remains, a system frozen by the act of looking, a system held in place by the insistence of repeated questions. A universe that responds to inquiry, even if the mechanism is purely physical, even if consciousness is not required. The symbolism is difficult to ignore, because in the smallest spaces of the quantum world, watching matters, asking matters, probing matters, the universe reveals its secrets only reluctantly, and sometimes only when we stop asking. And yet, this is where the mystery gently deepens, because the boundary between measurement and observation, between detector and awareness, between interaction and experience, is still not fully understood. Physics draws the line in one place, philosophy draws it in another, and consciousness, quiet, ungraspable, hovering at the edges of understanding, remains somewhere in between, not proven essential, not proven irrelevant, a presence that lingers just outside the mathematics, inviting questions, inviting wonder, inviting the possibility that a deeper layer may still be waiting beneath the equations. But those ideas lie elsewhere. Later, for now we remain inside the effect itself. The stillness, the freezing, the quiet truth that reality slows when examined too closely, a truth that hints at how delicate the quantum world is, how fragile its unfolding can be, how easily its motion can be reshaped by the act of simply looking. There is more to explore, the subtler experiments, the deeper interpretations, the poetic analogies that soften the physics into dreamlike imagery. There is a gentle paradox at the edge of this phenomenon. A paradox born from the rhythm of interruption, a paradox that tells us the universe can be urged into stillness by the simple repetition of asking the same question over and over again, not with curiosity, not with intention, but with the mechanical insistence of measurement itself. And to continue drifting into this strange effect, we settle deeper into the texture of rapid observation. The quiet mechanics behind the stillness, the slow realization that the quantum world does not move in the way intuition expects. When we imagine a system evolving, we often picture smoothness, a gradual unfolding, a continuous transition from one configuration to another. But the quantum world moves differently. Its evolution is probabilistic. It does not glide like a planet in a stable orbit. It spreads. Its wave function radiates into possibility space. Different outcomes slowly becoming more or less likely. And this spreading takes time. Even the smallest shift requires a faint, finite interval of evolution. A breath, a moment, a softness of motion that is easily cut, easily interrupted. If a measurement arrives before that motion has had any chance to develop, there is almost no probability that the system will have changed. So the measurement finds it exactly where it began, and collapse returns it to that same state. As if the system were trying to rise, and each measurement gently pressed it back down, a hand upon the shoulder, light but persistent, not forceful, not aggressive, simply interrupting just enough. To feel the effect more deeply, we drift into an image. Imagine a small particle trapped inside a potential well, a place where it can remain, but where quantum mechanics allows it to eventually tunnel out, to slip through a barrier it should not cross. If the system is left to itself, the wave function spreads outward, thinly, softly. A small piece emerges on the other side, a small chance that the particle appears outside the well, and over time, with enough repetitions of this quiet spreading, the particle will eventually tunnel, it will escape, but introduce measurements, rapidly, continuously. Each measurement collapses the wave function back into the interior, erasing the outward drift, resetting the evolution, over and over. So the probability never rises, the chance never accumulates, and the particle remains trapped, held not by walls but by attention, by collapse, by the quiet pressure of being asked too frequently to reveal its state. The universe disallows escape under constant questioning, a poetic truth, rooted in mathematics, but delicate enough to feel like metaphor. This is the heart of the quantum Zeno effect, a system that cannot change if it is never given time to begin changing, a wave function that cannot spread if it is forced constantly back to its origin, a process that cannot unfold if it is cut again and again into smaller pieces, pieces so small that evolution never gains traction, never lifts itself into a new configuration, never allows probability to drift outward. The effect is not mystical, it is not supernatural, it is simply a consequence of how quantum mechanics handles time, and how collapse interrupts motion. Yet even when grounded in pure physics, there remains something quietly haunting about the idea, something that feels as if the universe is capable of hesitating, as if the quantum world can be held in a poised state, a state of almost becoming, almost changing, almost evolving, but never quite crossing the threshold, held in a narrow valley of possibility, not because nature wants to stay still, but because collapse forces it to start fresh each time, as if memory is erased, as if the system cannot accumulate any momentum, any unfolding, any drift. Without a pause between measurements, a pause that rapid probing refuses to allow. Experiments brought this quiet mathematics into the real world. Physicists prepared atoms that would naturally transition from one energy state to another. Left alone, the transition would occur, predictably, smoothly, in accordance with the probabilities, but when measured at high frequency, the transition stalled, slowed, sometimes halted entirely. Like a pendulum touched so lightly and so frequently that it cannot swing, the atoms remained in their initial states, held by collapse, held by interruption, not by intention, but by the structure of the interaction. Each measurement resetting the wave function, each collapse discarding the small drift that evolution was trying to nurture, and the system stayed still, quiet, almost suspended, at the boundary between potential and actuality. This stillness, confirmed again and again, gave rise to a subtle philosophical tension, because physicists could point to the formal mechanism, repeated collapse, interrupted evolution. But the public imagination, less constrained by precision, saw something else, a system that froze under observation, a reality that refused to change when watched, a universe that responded to attention, and from that grew interpretations, narratives, and speculations, some playful, some poetic, some deeply earnest, the idea that consciousness itself was the cause, that awareness held the system still, that the act of mental observation was the force behind the effect. But the physics is quieter, more humble, more grounded. Measurement is physical. A detector is not a mind. A sensor is not awareness. A photodiode does not possess consciousness. Yet it freezes systems all the same. The quantum Zeno effect emerges not because a mind observes, but because any interaction that extracts information interrupts evolution. Consciousness does not need to enter the picture. And yet, the poetic allure remains, because the effect demonstrates something profound, something subtle, something that invites metaphor, that observing, in the broadest sense, changes what is observed, that attention has structure, that inquiry has consequence, that probing reshapes unfolding, even if the observer is merely a machine. Even if consciousness is nowhere involved, the symbolism lingers, the universe holding still beneath steady watch. The subtlety grows deeper when we drift into the closely related idea of continuous monitoring. Because rapid measurements are only one way to freeze motion, there is a softer method, a gentler form of watching, where the system is not poked repeatedly, but monitored constantly, as if bathed in a faint glow of observation. An environment that continuously interacts with the system, extracting information, but not sharply, not discreetly, not with abrupt collapses. Instead, the system is nudged, guided, shepherded, its wavefunction kept narrow, kept aligned, kept close to its starting point. This continuous observation creates a similar freezing, a similar slowing, a similar stillness, one achieved not through violent collapse but through a gentle stream of micro-interactions, a soft rainfall of information, holding the system in place, and this soft version of the effect invites an even more dreamlike analogy. Imagine a candle flame, left alone in a quiet room. It flickers, wanders, breathes, tiny air currents shift it, microscopic turbulence shapes its dance. But imagine now a watcher, not a conscious watcher, just a presence, a sensor, a field, something that monitors the flame continuously, gathering information, moment by moment. That monitoring can steady the flame, not because it is being held, not because intention is being applied, but because the act of monitoring removes uncertainty, dampens motion, constrains freedom. The flame cannot wander. It becomes still, a small glowing point of quiet stability. This image is only a metaphor, but it reflects the gentle spirit of the effect. Observation, in the quantum sense, steadies the system, prevents wandering, prevents spreading, prevents change. The quantum Zeno effect carries another layer of subtlety, one that deepens the conceptual intrigue. It has a reverse, a partner, a dual phenomenon, sometimes called the anti-Zeno effect, where rapid measurements do not freeze motion, but accelerate it, a system that changes faster because of being measured, because collapse pumps probability into new regions, because interruption creates new paths. This reversal reminds us that the quantum world is not simple, not binary, not obedient to intuition. Interaction can slow, interaction can accelerate, and the boundary between stillness and motion, between freezing and flow, is delicate, subtle, context-dependent. The world of the very small responds to touch in nonlinear ways. Sometimes gentle probing holds it in place. Sometimes it nudges it forward. Sometimes it creates pathways that did not exist. And sometimes it closes doors before they open. All of this, the freezing, the slowing, the subtle acceleration, arises from one principle. Measurement changes the system. Even if the measurement is just a brush, a whisper, a hint, even if the measurement leaves no conscious record, even if no mind ever sees the result, the system is changed. The universe reacts, not because it cares who is watching, but because observation is interaction, and interaction is evolution, intertwined, woven, unavoidable. There remains one more layer to explore, one final deep analogy, one final shimmer inside this phenomenon. There is a final layer beneath all of this stillness, a quieter, subtler dimension of the quantum Zeno effect, a layer that pulls us toward the deepest part of its mystery, a layer not about numbers or probabilities or formal equations, but about what it means for reality to be interrupted, again and again, so often that the flow of time itself seems to falter, so often that becoming is replaced by remaining, so often that motion gives way to stillness. Not because anything holds the system down, but because change requires continuity. Evolution requires space. Probability needs room to stretch, to wander, to lean toward a different outcome, and rapid measurement cuts that space, slices time into smaller and smaller intervals, intervals so thin that change has no foothold, like trying to take a step on ground that crumbles into dust the moment you place your weight upon it, a world with no solid surface for motion. Just a series of restarts, resets, beginnings that lead only to new beginnings, never to the next moment, never to the next state, never to the next unfolding. And so we drift into the last deep analogy, the final image that helps the mind feel what the equations describe. Imagine standing before a doorway leading somewhere different, somewhere new, a place the system has a natural tendency to enter, not urgently, not violently, but gradually, softly, like probability flowing through a channel, but each time you step forward, a soft voice calls your name, you turn back, and when you look again, the doorway has reset, the threshold has returned to its original state. No progress made, no distance gained, only the beginning recreated, over and over. And if that voice calls often enough, if it interrupts without rest, you never step through, not because you do not want to, not because you are prevented, but because the motion never has time to accumulate, possibility never grows, transition never forms, the next state never becomes more likely, because every instant is a return to the start, a fresh beginning, a zeroing out. This is the essence of the effect, the delicate mechanism behind the stillness, a world held at the edge of change, unable to cross it, because the interruptions are too frequent, too steady, too absolute. What experiments revealed is that this is not poetry, not metaphor, not imagination. Atoms behave this way, photons behave this way, quantum spins, energy states, tunneling particles, all behave this way. All show that the flow of probability is fragile, easily disrupted, sensitive to any extraction of information, as if the universe insists that to observe is to intervene, that to measure is to reshape, that to extract information is to alter the unfolding of what could have been, and the quantum Zeno effect is simply the most extreme expression of that truth, a truth that tells us the world is not passive, not inert, not merely waiting for us to look. The world responds, always, inevitably, even when no mind is involved, even when detection is mechanical, automatic, unaware. Even then, the universe reacts and reality rearranges itself. This leads to a profound reflection, a soft meditative insight at the boundary between physics and philosophy, not a claim, not a conclusion, just a quiet recognition that in the quantum world there is no such thing as a neutral glance. No such thing as a harmless observation, no such thing as a perfect separation between the system and the act of examining it. To observe is to touch, to measure is to influence, to extract knowledge is to reshape the space of possibilities. And the quantum Zeno effect is the whisper of that truth, amplified, made visible, turned into a slow, frozen tableau, a demonstration that even pure attention, stripped of consciousness, stripped of intention, has consequence. Not because the universe needs a mind, but because the universe is relational, interactive, entangled, connected, intricately sensitive to the smallest exchanges of information, so sensitive that a system watched too closely cannot move, and a system allowed to breathe can drift into new forms, into new states, into new outcomes. When the effect was first discovered, many wondered what it meant, what it revealed, what it whispered about the nature of observation. Some wondered whether consciousness had a special role, others insisted it did not. But beneath all debate, beneath all interpretation, beneath all philosophical extension, the effect stands as a reminder, a soft, steady reminder, that reality is not made of things that exist in isolation. It is made of relationships, between systems, between particles, between measurement devices, between environments, between all the subtle channels through which information flows. And whenever information is exchanged, whenever knowledge is extracted, whenever distinction is created, something changes. The wavefunction narrows, possibility contracts, the future tilts, and the system becomes different from what it would have been. Even if the change is only stillness, only a pause, only the refusal to take the next step, the effect becomes even more fascinating when we consider its experimental reach. Researchers learned to control transitions by adjusting the rate of measurement. Slow measurements allow motion. Rapid measurements block it. Intermediate measurements reshape it. It is like tuning the tempo of reality. Fast enough and the system freezes. Slow enough and it flows. In between, there are patterns, oscillations, delicate rhythms, a choreography of evolution and collapse, as if the system were dancing to the beat of observation, a dance whose tempo we can change, a dance whose structure is written in the mathematics of possibility, a dance that reminds us how deeply the quantum world depends on how we look at it, not mentally, not consciously, but physically, with detectors, with fields, with any mechanism that can gather the smallest trace of information. There is one last nuance, one final shimmer inside this effect, a deeper way to view the stillness through the lens of survival probability, because what we call freezing is really a slowing down of decay. A decaying state, a particle likely to transition, can be held in its initial condition if measured rapidly. Its survival becomes almost guaranteed, not because it gains strength, but because it loses the opportunity to change. The space for decay is cut, fragmented, reduced to slivers too small for probability to escape through. It is like sealing a vessel with countless microscopic lids. Every time one opens, collapse closes it. Every time one pathway appears, measurement erases it, and the particle remains still, quiet, persistent, the universe allowing it to last far longer than it would naturally, because the pathways of transition are never allowed to form, never allowed to accumulate, never allowed to grow. All of this completes the picture. All the ideas woven through this effect have now settled. The phenomenon itself, the mechanism, the experiments, the misinterpretations, the popular claims, the subtle corrections, the candle analogy, the continuous monitoring, the anti-Zeno reversal, the philosophical reflection, the survival framing, everything has unfolded, everything has been explored, everything has been softened into place. And so now, with all pieces of this section fully discussed, we drift gently, quietly, naturally, to the next mystery, the next doorway, the next shimmering space in the quantum landscape, where multiple observers may not agree on what happened, where reality may not be the same for everyone, where truth becomes relative, and where the universe reveals another layer of its dreamlike nature. There is a quiet strangeness that settles over the mind when we reach this part of the quantum landscape, a kind of soft bewilderment, a drifting sensation, as if the ground beneath thought were becoming fluid, as if truth itself were beginning to shimmer. Because here, in this thought experiment, the universe reveals something almost impossible to believe. The idea that two observers, standing in the same world, measuring the same event at the same moment, may not agree on what happened, not because one is mistaken, not because someone misread a device, but because reality itself might not be single, not definite, not universal. It may depend on who is looking, on what information they have access to, on what part of the system is sealed away, on how deeply their knowledge reaches into the quantum state. This is the world of Wigner's friend, a world where truth divides, where facts become relational, where what is real for one observer may not yet be real for another, and where the mind is invited to drift into the possibility that the universe does not share a single, absolute narrative, but instead whispers different stories to different observers, quietly, consistently, mathematically, without contradiction. As long as those observers cannot compare their notes, imagine a small room, a closed laboratory, completely sealed. Inside it, a friend, calm, focused, performing a simple quantum measurement, perhaps observing the polarization of a single photon or the spin of an isolated particle. A measurement that, by all ordinary standards, produces a definite result, up or down, left or right, one outcome gently realized out of the haze of possibilities. Inside that room, the friend sees a number, a fact, a clear event, a result that becomes part of their memory, their mind, their experience. For the friend, the wave function has collapsed. The uncertainty is gone. Reality has chosen. But outside the room, Eugene Wigner waits, quietly, patiently, treating the entire laboratory, the equipment, the particle, and even the friend, as one unified quantum system, a system he has not yet interacted with, a system still untouched by his knowledge. And for Wigner, the wave function has not collapsed. It continues to evolve, spreading, branching, holding inside it the possibility that the friend saw outcome A, and the possibility that the friend saw outcome B, both possibilities still alive, still valid, still woven into the mathematical state. For Wigner, his friend is in a superposition, not psychologically, not experientially, but physically, quantum mechanically, a superposition of having measured one result and having measured the other. It is not that he imagines two minds in conflict. It is that the entire system remains uncollapsed, because he himself has not yet received any information, not a signal, not a message, not a clue, nothing that could force the universe to narrow its state, nothing that would allow him to conclude that a single outcome has occurred. So for Wigner, the room is still a cloud of possibilities, still a wave function, still a set of overlapping branches. Even though his friend is absolutely certain that one branch has already happened, this is the paradox. One observer believes the universe has chosen, the other believes it has not. Two realities peacefully coexisting, both internally consistent, both following the same equations, both correct from their own vantage point, both irreconcilable until communication occurs. And the moment communication happens, a collapse, a narrowing, a transition from duality to singularity. The moment Wigner learns what his friend saw, the wave function sharpens, the possibilities shrink, the two realities merge into one, the storylines converge, and the paradox dissolves. Not because one reality was false, but because both were valid, until knowledge forced them into agreement. There is something both unsettling and beautiful in this idea, the quiet suggestion that the universe may not commit to a single version of an event, until observers compare their experiences as if facts are not absolute, but relational, as if reality waits for the exchange of information, as if truth is not a single thread, but a collection of parallel strands, braiding together only when observers interact. Only when knowledge flows, only when perspectives meet. Before that, each observer carries their own unfolding, their own wave function, their own version of what is real, and none of them are wrong. Not yet, not until they speak. The strange power of this thought experiment comes from its simplicity. Nothing exotic, nothing mystical, just two observers, one inside a room, one outside, and a single quantum measurement, yet the mathematics demands this strange duality, this coexistence of incompatible truths, this softness in the structure of reality. And when Wigner first proposed it, he wondered, softly, carefully, whether consciousness itself was the key, whether awareness was required to bring collapse, whether the friend's mind played a fundamental role. He imagined that consciousness ended the superposition, that subjective experience forced a choice, that the universe could not hold multiple outcomes in the presence of a conscious observer. But the equations do not say that. They never did. They simply say that the collapse depends on information, on interaction, on the flow of distinguishable facts, not on minds, not on awareness, not on perception, but on whether something in the world records which branch occurred, a detector, a surface, a photon, a machine, a memory. Even a single environmental particle can be enough, which means the friend's consciousness is not required. It is simply an example, a placeholder, a vivid way to illustrate the deeper truth, that reality is not globally objective, that quantum events are not universal facts, that different observers can legitimately assign different states to the same system, and all of them can be correct, as long as their knowledge remains separate. This is the quiet power of Wigner's idea, a gentle, mathematically precise challenge to the classical belief that reality is the same for everyone, a soft invitation to imagine a world where truth is dependent, contextual, observer relative, not because the universe is chaotic, not because it is subjective, but because information is local, and no observer has access to the whole, not instantly, not universally, only gradually, through interaction, through communication, through the slow entangling of knowledge. And in this space, something deeper begins to stir, a realization that what we call facts may not be carved in stone. They may be woven in relationships, in connections, in who knows what and when, and how. A realization that truth in the quantum world is not a monolith, but a tapestry. Different threads held by different observers, different branches coexisting, until they are brought into alignment, through the sharing of information, through the collapse that happens when perspectives meet, when one observer learns what the other has seen. All of these ideas have been opened, the doorway now revealed, and the thought experiment has only begun. There is more to explore, more to untangle, more to soften into understanding. The deeper paradox, the modern extensions, the newer arguments that stretch this scenario to its limits. But that belongs to the next movement, the next unfolding, the next slow and dreamy descent into the nature of relative facts. In the softness of this thought experiment, there is a quiet figure standing in the center, consciousness, not as an answer, but as a question. When Wigner first imagined his friend in the sealed laboratory, watching a quantum event unfold, he did not only see equipment and particles, he saw a mind, a conscious experience, a person who would look at a detector and genuinely feel, I saw this outcome, and not that one. For that friend, there is no superposition, no branching, no ambiguity. There is a single, vivid fact, a memory written into the neural patterns of a living brain. And Wigner wondered, could that very act, the birth of a conscious experience, be what forces the universe to choose? Could awareness itself be the line that divides the quantum fog from classical clarity? Before the friend looks, the photon is in a superposition. After the friend looks, the mind reports a definite result, perhaps, Wigner thought. That is when collapse happens, not at the detector, not in the electronics, not in the environment, but in the mind, in the interior space where experience arises, in the moment when something in the universe not only registers a number, but feels it, knows it, lives it. This idea is called consciousness causes collapse, a phrase that sounds dramatic, but is really a question in disguise, a gentle suggestion. What if? What if the equations must be supplemented with something non-physical? A rule that says, when awareness occurs, the wave function collapses. And so, inside the sealed lab, the friend's conscious perception would force the universe to pick one outcome. While outside, Wigner's own description would still treat the entire room as a superposition, not because nothing has happened, but because he has not yet accounted for the friend's consciousness. He has not yet included that extra ingredient. He has not yet updated his description to reflect the mental event. There is a tension here, a soft split, between two views, one in which consciousness does something fundamental to the quantum world, and one in which it does not. If consciousness really does cause collapse, then the friend inside the lab is living in a universe where the photon's fate is already decided. The wave function has reduced. The outcome is a solid fact, and Wigner outside is simply ignorant. His superposition is not a real physical state. It is just a representation of his lack of knowledge, a bookkeeping device, a mathematical expression of uncertainty. The friend's reality is the true one. The conscious observer has already forced nature to choose, and Wigner's superposition is an artifact of incomplete information. In this view, there is a hidden hierarchy. The consciousness inside the room has priority. The experience of having seen an outcome is what truly changes the universe. Everyone else is just catching up. But if consciousness does not cause collapse, if the equations of quantum mechanics are complete by themselves, if no special mental ingredient is required, then the picture changes. The friend's experience becomes just another process. Neurons firing, synapses strengthening, ions flowing, all of it. Every detail of the brain is part of a larger quantum system, and that system can remain in superposition, even though the friend feels completely certain. In this view, the wave function is not about ignorance, it is about reality. Wigner's description of his friend in superposition is not a temporary placeholder. It is the true quantum state, a state in which different conscious experiences coexist, not side by side in one mind, but as different branches of one unified system, waiting for Wigner himself to interact, to measure, to entangle, to become part of whatever outcome he eventually learns. This is where the paradox sharpens. If consciousness causes collapse, then whose consciousness matters? The friend's, who sees the result first? Wigner's, who includes the whole lab in his reasoning? Both? Neither. Does collapse happen once, at the moment of the friend's perception? Or twice, once for the friend, once for Wigner? Or does it happen whenever any consciousness becomes aware? And if so, how does the universe coordinate these moments? How does it ensure that all conscious observers agree on the same history, that no one remembers an outcome that others never see? These are not technical questions. They are structural. They ask, Can we really attach a fundamental physical process to something as elusive and poorly understood as consciousness? Can we base the most precise theory in physics on something we do not yet know how to define, on something we cannot yet measure, predict, or formalize? Many physicists feel uneasy with that idea. They prefer a universe where consciousness emerges from physical processes. Not one where it changes physical processes. They prefer to let the equations speak. And the equations do not mention minds. They mention states, operators, Hamiltonians, interactions, information. So an alternative view grew stronger. The view that collapse is not about consciousness. It is about correlations, about the spread of information into the environment, about the way systems become entangled with their surroundings, so that different outcomes can no longer interfere. In this picture, when the friend measures the photon, the lab's internal environment records the result. Detectors click, amplifiers ring, molecules vibrate, air scatters light, the walls absorb heat. Bit by bit, the information about the outcome seeps into millions, billions, trillions of microscopic degrees of freedom. Until the two branches, one where the friend saw outcome A, one where the friend saw outcome B, have become deeply separated, decohered, unable to recombine. For all practical purposes, each branch is now its own self-contained world. Even if, in principle, the global wave function still holds them both, from inside one branch, the friend feels a single reality, a definite outcome, a clear memory. They never feel split, never feel smeared, never feel like a superposition, because their consciousness arises within one branch, not across all of them. From their perspective, the universe has collapsed. Even if the global state is still broad, still branching, still containing other outcomes that are now inaccessible. For Wigner outside, who has not yet interacted with the room, both branches are still part of his description, both versions of the lab, both versions of his friend, both are present in the wave function, and until he opens the door, asks the question, and hears the answer, his reality remains split, not in experience, but in the mathematics. This leads to a softly radical idea that collapse is not a physical jump, not an actual abrupt change in the world, but a change in description, a shift in perspective, a narrowing of the effective state from the viewpoint of a particular observer. When the friend sees the result, their own state of knowledge collapses. When Wigner hears the friend's report, his state of knowledge collapses. Each observer updates their own description. Each has their own wave function, their own assignment of probabilities, their own accounting of possibilities. And those descriptions need not be identical until they exchange information, until they interact, until they share what they know. Reality becomes relational, facts become relative, not in the sense that anything goes, but in the precise sense that what is real for one observer is what they can consistently describe given the information available to them. From this viewpoint, Wigner's friend is not a paradox, it is a demonstration. That physics may not describe one global, absolute reality, but a web of consistent perspectives, each tied to an observer, each defined by what that observer has interacted with, each collapsing only when knowledge changes. And this idea has been pushed further, stretched, refined, tested, not yet in full experiments, but in sharper thought experiments. One of the most striking is the Frauchiger-Renner scenario, a kind of extended version of Wigner's friend, with more observers, more layers, more opportunities for disagreement, a careful arrangement in which different observers apply quantum mechanics to each other, assign different states, draw different conclusions, and end up with predictions that cannot all be true at once. Unless we give something up, unless we surrender at least one of our classical intuitions. In the Frauchiger-Renner construction, there is not just one friend. There are multiple, each in their own lab, each making measurements, each with their own Wigner-like observer outside, each assigning wave functions, each drawing inferences. They all use the same theory, they all follow the same rules, and yet, when their conclusions are compared, there is a clash, a logical tension, a soft but undeniable statement that we cannot have all of the following at once, a single, observer-independent reality, universal validity of quantum mechanics. In classical reasoning about measurement outcomes, at least one must be surrendered or weakened or reinterpreted. We can keep a global reality, but then perhaps quantum theory cannot be applied to observers themselves. We can keep universal quantum theory, but then perhaps reality is not single. Or perhaps we can keep logic and quantum theory, but reality becomes relational. Different observers hold different consistent stories. And there is no global story that includes them all without contradiction. Relational quantum mechanics embraces this. It says, a fact is always a fact for someone. A measurement outcome is always relative to the system that recorded it. There is no view from nowhere, no universal ledger of events, only a network of interacting observers, each with their own internal record, their own past, their own sequence of outcomes. And physics does not choose one record as the absolute truth. It simply ensures that whenever two observers compare notes, their stories can be made consistent, even if, before they meet, their descriptions are different. In this view, Wigner's friend inside the room and Wigner outside are both right. The friend is right to say, I saw a definite result. Wigner is right to say, I must treat you as a superposition until I learn your result. They are speaking about reality relative to themselves, relative to what they know, relative to what they have touched. And there is no deeper observer-independent snapshot of the world that both must match. Only the requirement that when they communicate, when information flows, their descriptions interlock, their narratives merge, their facts align. In the darkness of the sealed lab and in the quiet of the outer corridor, two realities coexist, waiting for interaction, waiting for the exchange of information, waiting for the moment when multiple perspectives knit together, not into a single pre-existing truth, but into a shared relational structure, a pattern of agreements, a web of consistent memories, held by beings who are themselves physical systems, subject to the same quantum rules. And this thought, this gently radical view, leads us ever closer to the central question. If facts can be relative, if observers can disagree about the structure of reality, and yet all remain consistent within their own vantage point, then what role does consciousness play, if any, in choosing which reality we inhabit? And what does it mean to say that the universe is, when what is may depend on who is asking, and when and how you breathe and drift with these questions into deeper stillness? There is a quiet moment in the unfolding of this paradox where everything feels as though it is holding its breath, a moment where two stories, two observers, two descriptions of the same event float side by side, neither wrong, neither incomplete, just differently anchored, each one shaped by the information the observer carries, each one shaped by what they have touched, measured, learned, and woven into memory. In the sealed room, the friend stands before the detector. The outcome is clear, sharp, immediate. A definite number is etched into their awareness. A moment ago, the photon was a superposition. Now in their mind, there is a single truth. It feels absolute, final, as though the universe has chosen a path, committed to it, and written it into the fabric of their conscious experience. Outside the room, Wigner holds a different picture. For him, nothing has yet become definite. He has not opened the door. He has not asked what the friends saw. He has not entangled himself with their memory. And so, his best description remains broad, a wave function with multiple possibilities still alive within it, a calculation that has not yet narrowed, a superposition that reflects not chaos, but a lack of information. It is not ignorance in a careless sense, but the deep, structural, quantum kind, the kind baked into how information travels, how entanglement spreads, how observers remain isolated from one another until the universe allows their knowledge to merge. This duality, this strange coexistence of two valid pictures, is not a contradiction. It is a clue, a hint that the universe may not carry a single global state that applies to all observers at once. Instead, each observer holds their own slice of reality, their own conditional truth, their own branch of the universal story, not because reality is subjective, but because information is local, interaction is finite, and what is real for one observer is what they can consistently predict and remember, until they touch another observer's story, and the two threads lock together, merge, form a larger structure, a shared world. When Wigner finally opens the door, when he speaks to the friend, when the answer reaches his ears or eyes or instruments, something subtle happens. The two descriptions, the broad and the narrow, the superposed and the definite, collapse into one. But it is not the universe collapsing. It is not a cosmic switch flipping. It is not a physical jolt echoing across the lab. It is a unification of knowledge, a merging of information, a syncing of two previously isolated perspectives. What collapses is the gap between observers, not the underlying reality. This is one of the profound insights behind relational quantum mechanics, that events do not have absolute meaning. They have meaning relative to the systems they affect. A measurement is a fact for the observer who records it. A different observer who has not yet encountered that record may assign a different state. And both descriptions are valid, not metaphors, not approximations, but physically meaningful, as long as each observer uses their own information, their own interactions, to define what reality is. This idea is unsettling at first. We are used to thinking of the universe as a single shared object, a vast three-dimensional arena in which events occur whether we see them or not, a world that stands outside us, independent of us, neutral, objective. But the quantum world does not bow to that intuition. It does not easily fit into a single observer-independent frame. It is built from relationships, from correlations, from the way systems become entangled as they interact, and from the way those entanglements spread outward, weaving a tapestry of conditional truths, each one anchored to an observer, each one consistent within itself, and each one waiting to merge with others. When information is shared, when communication flows, when the universe reveals one more thread, Wigner's friend is not just a puzzle, not just a curiosity. It is a doorway, a window into a deeper question. What does it mean for something to be real? If reality depends on who knows what, and when they know it, if facts are relational, if truth is something built through interaction, not something that exists fully formed and absolute. To appreciate this, it helps to imagine a variation of the experiment. Imagine that Wigner does not open the door. Not now, not ever. Imagine that the friend records the result, writes it down, stores it carefully, but never tells anyone. No message is sent, no signal escapes, no photon leaks out. The internal environment of the lab contains the outcome. The friend's memory contains the outcome, but the outside world does not. For Wigner and all external observers, the lab remains in superposition. A sealed box, a quantum island, completing its own internal history, independent, isolated, a separate branch of possibility, until the moment of interaction arrives. If it ever does, this is not philosophy, it is physics. It is how quantum theory tells us the world is structured. States are global, but information is limited, and each observer has access to only a thin slice of the whole. Each slice is a consistent story, a personal narrative written from their own interactions. Not because consciousness distorts reality, but because interaction defines it. Knowledge shapes it, observation carves it. Until different observers share information, they inhabit different affective worlds. This is the heart of the paradox. And the beauty, Wigner's friend is not a contradiction. It is a reminder that the universe may not grant us a single absolute version of events. It may give us a web, a network, a mosaic of perspectives, each one partial, each one true, each one woven from what has been touched, measured, and known. This does not deny an external reality, it simply reframes it. Reality is not a monolith, it is not a fixed ledger, it is a structure of correlations, a shifting geometry of information, a tapestry woven from interactions. And consciousness, if it plays any role, does not do so by forcing collapse, but by housing a particular thread, a particular vantage point, a particular internal mirror of the universe. One that is finite, conditional, beautifully limited, and deeply connected to everything it observes. From here, the next step in the journey becomes a natural one. If different observers can hold different but consistent realities, if measurement is tied to interaction, if truth is relational, then what does this mean for the interpretations that try to explain quantum mechanics itself? Interpretations that attempt to say what the wavefunction is, what collapse means, whether consciousness plays a role, or whether the universe is forever branching, forever guided, or forever collapsing according to hidden rules. To see this clearly, we must drift softly into the deeper forest of quantum interpretations, where consciousness, information, and the shape of reality intertwine. There is a quiet moment where the mind drifts between curiosity and rest, and the universe seems to soften around the edges. In that stillness, questions appear that feel almost alive, as if they've been waiting for someone to notice them. One of those questions sits at the center of quantum theory, glowing gently, shifting its outline depending on how we look at it. It is the question of how we should interpret the act of measuring the world, and whether the observer, the one who sees, the one who holds information, plays a fundamental role in shaping what is real. Quantum mechanics gives us equations of exquisite precision, predictions that match experiments to extraordinary accuracy, yet it remains strangely silent about what those equations mean. So scientists and philosophers have spent decades, even generations, trying to build interpretations around those equations, like different lanterns that illuminate the same landscape from different angles. And among those interpretations, some appear to leave a space, a doorway, through which consciousness might matter in a deep way, not as magic, not as mysticism, but as something woven into the architecture of how reality unfolds. The first of these interpretations emerged in the early 20th century, when quantum theory was still young, and its implications were startling enough to reshape the foundations of physics. It became known as the Copenhagen interpretation, named after the city where Niels Bohr, one of the central figures of quantum mechanics, developed his ideas. It's not a single unified doctrine, but more of a philosophical framework, a way of thinking about quantum phenomena that emphasizes the role of measurement. In this view, a quantum system does not possess definite properties, at least not in the classical sense, until it interacts with a measuring device. Before that moment, its state is represented by a wave of possibilities, a smooth, mathematical distribution of outcomes. But when a measurement happens, that distribution seems to narrow, selecting one outcome. This is the essence of what people call collapse, not a physical explosion, not a sudden violence in the fabric of the world, but a transition, a shift from uncertainty to definiteness. The Copenhagen interpretation doesn't say that consciousness triggers this change, but it does say something subtle and profound. It says the very act of measurement, the moment information becomes available, is what matters. This raises a gentle but persistent question, one that echoes softly through the philosophy of physics. What exactly is a measurement? Is it a physical interaction, like a particle hitting a detector or a photon being absorbed by an atom? Or is it something that only becomes meaningful when a conscious observer becomes aware of the result? Some physicists lean toward the first answer, arguing that measurement is simply another kind of physical process, complex, yes, but nothing fundamentally mysterious. Others, including thinkers like Wigner in his earlier years, felt drawn toward a different idea. In his view, consciousness had a unique role in the transition from possibility to reality, as if awareness itself were a boundary, a place where the world finally makes a choice. He imagined an extended chain of physical interactions. A particle affects a detector, the detector affects a measuring apparatus, the apparatus sends a signal to a brain, the brain processes the signal. But where along this chain does collapse occur? John von Neumann, another giant of early quantum theory, proposed that the entire chain could be treated quantum mechanically, right up until the final step. The only remaining candidate for a non-physical boundary, in his reasoning, was the moment of conscious experience. He didn't claim this was proven, or that consciousness must be something supernatural, only that in a universe built from quantum interactions, awareness seemed to stand apart, distinct from the mathematical description. This idea became known as the von Neumann chain, and at its end sits the so-called cut, the place where descriptions change from quantum to classical, from probabilities to definite outcomes. The location of that cut has never been settled. Some interpretations push it down into the physical world, arguing that collapse happens well before a mind becomes involved. Others allow the cut to drift upward, toward the moment an observer becomes aware, toward consciousness itself. This ambiguity gives rise to a profound tension, a quiet uncertainty that lies at the heart of how quantum theory is understood. And yet, even among physicists who prefer a more physical explanation, there is a recurring theme: information. Information seems to matter, deeply, in a way classical physics never required. This is where interpretations like cubism come into the story, bringing with them a distinctly personal flavor. In cubism, a measurement outcome is not a property of the world alone, but a personal experience for the observer. The wave function isn't a physical object in this view, but a mathematical tool an observer uses to track their expectations, their beliefs, their likely encounters with the world. Under this interpretation, quantum mechanics becomes almost subjective, not in a whimsical or arbitrary way, but in a way that highlights the role of the agent, the one who assigns probabilities, the one who receives the outcomes. It's not that consciousness causes collapse, but that quantum mechanics is a theory about the experiences of observers, not about an objective, observer-free reality. This interpretation gently shifts the focus from the world out there to the interplay between the world and the knower. The universe becomes participatory, not in the mystical sense, but in the informational sense. There are other interpretations that echo this relational theme, that suggest facts themselves may not be absolute, but depend on the perspective of the observer. Relational quantum mechanics proposes that quantum states, measurement outcomes, and even the definiteness of events exist only relative to an observer or system. In this view, there is no single, universal description of reality that all observers must share. Instead, each observer has their own network of facts, their own consistent tapestry of measurements and interactions. Two observers may describe the same system differently, and both descriptions can be equally valid. Without contradiction, because reality is not a monolithic structure, but a web of relations. This idea aligns naturally with the subtleties revealed by thought experiments, like Wigner's friend, where observers can disagree on what is real, and no single viewpoint is privileged above the others. It's not that consciousness exerts a force on the world, but that the concept of reality, its definiteness, its solidity, depends on the observer's frame of reference. As the mind drifts through these interpretations, a gentle pattern begins to emerge. Some interpretations place measurement at the center, highlighting the role of information, the transition from potential to actual. Some allow consciousness to sit near that transition, as if awareness were the final step in the chain. Some treat the wave function not as a physical wave, but as a reflection of the observer's own knowledge, their expectations, their experiences. Others loosen the very concept of an objective fact, suggesting that each observer carries their own version of events, their own thread of reality. For all their differences, these interpretations share a quiet recognition. The observer cannot be ignored. Whether consciousness causes collapse, or whether collapse happens long before awareness appears, or whether collapse is only a convenient description, each interpretation must decide how the observer fits into the picture. And in making that decision, each interpretation reveals a different facet of the quantum world, like rotating a crystal and watching new colors shimmer across its surface. This is why the question feels so profound, so strangely intimate. It's not merely a question about particles or waves or equations. It's a question about our place in the universe, about the relationship between mind and matter, between knowing and being, between observation and existence. And as the mind settles deeper into the quiet rhythms of thought, one more insight begins to surface. These interpretations, the ones that leave space for the observer, are not claiming certainty. They are not declaring that consciousness creates reality, or that observers pull outcomes into existence. Instead, they highlight the open edges of quantum theory, the places where the mathematics fades into philosophy, where the equations leave room for interpretation, for wonder, for the possibility that reality might not be fully independent of the observer. And within that possibility, something beautifully mysterious remains. The sense that the universe is not merely a machine, grinding through predetermined motions, but a tapestry of interactions, relations, information exchanges, where the role of the observer is subtle, yet undeniable. And as these ideas linger, softly, like distant echoes, the mind drifts into the deeper layers of the interpretation, where questions grow more intricate, and the boundary between observer and observed becomes even more delicate. In the quiet places of thought, where ideas unfold slowly, and the boundaries between physics and philosophy begin to blur, the landscape of interpretations grows wider, more intricate, more dreamlike. We continue drifting through that landscape now, lingering gently on the interpretations that shape the way scientists think about measurement, about the observer, and about the strange bridge between potential and actuality. Among these interpretations, some lean away from consciousness, pushing it outward, toward the margins. Others keep it close, as if awareness itself might be woven into the structure of quantum events. And some, quietly, almost humbly, suggest that reality might not need collapse at all. One of the most influential alternatives to any consciousness-related picture is the many worlds interpretation. It begins from a simple idea, an idea both elegant and radically different from the collapse-based view. What if the wave function never collapses? What if the universe never chooses a single outcome, but instead allows every possibility to unfold? In this view, superposition is not a temporary state waiting to become definite. It is the true ongoing nature of the universe. When a measurement happens, the wave function does not contract. Instead, the observer and the system become entangled with one another, branching, separating, drifting into different versions of reality that can no longer interact. One version of the observer sees one outcome. Another version sees another. Each outcome is real, but each is locked into its own branch of the universal wave function. There is no need for collapse, no special role for observation, no boundary between quantum and classical, only a vast, ever-branching structure where all possibilities exist. In this interpretation, consciousness does not affect reality. Reality simply expands into more and more branches, more and more versions of events, with observers traveling within the branches that align with their experiences. The observer is not a creator, but a participant in an unfolding, universal wave. It is a picture of exquisite mathematical purity, and also one that feels strangely serene, as if the universe is not making decisions so much as allowing every possibility to gently blossom. Another interpretation takes a different path, one driven not by branching worlds but by hidden guidance, a deeper structure beneath the probabilities. This is the pilot wave interpretation, also known as de Broglie-Bohm theory. Here, particles always have definite positions, definite paths, even when we cannot see them. They move under the guidance of a wave, a real physical wave that spreads out through space and determines how each particle evolves. The wave can interfere with itself, creating patterns of probability, but the particle follows a single definite trajectory within that wave. There is no collapse here either. The wave evolves smoothly. The particle moves smoothly. Measurement does not create a new reality. It simply reveals the path the particle was already on, even though that path is influenced by the whole structure of the guiding wave. In this view, consciousness has no special role. Reality is determined by physical variables that exist independently of observers. Yet the guidance equation, the hidden layer beneath the quantum world, carries a soft strangeness of its own, suggesting that particles are influenced by the entire configuration of the universe, as if everything is quietly connected beneath the surface. There are also objective collapse theories, interpretations that preserve the idea of collapse, but shift its cause from observers to physical processes. In these theories, collapse is real, a physical event, but one that occurs spontaneously according to precise rules. A wave function might collapse because it reaches a certain size, or because mass accumulates beyond a threshold, or because a system interacts with gravitational fields in a particular way. In these models, collapse is not triggered by measurement or consciousness or awareness. It is a natural, built-in feature of the universe. A particle in superposition might collapse even if no one is watching, a kind of gentle, intrinsic narrowing of possibilities into facts. These theories are compelling because they make predictions that might someday be testable. They offer the hope of turning collapse from a philosophical puzzle into a physical phenomenon, something that could be measured, observed, recorded. In this view, consciousness plays no fundamental role. The universe chooses outcomes on its own, quietly, independently, following laws we have not yet fully understood. As the mind drifts through these various interpretations, a pattern becomes clear. Some interpretations give collapse a central place. Others deny its existence entirely. Some keep consciousness at arm's length. Others place it near the heart of the measurement process. Some treat quantum mechanics as a description of the world. Others treat it as a description of our knowledge of the world. Some create a universe that splits. Others create a universe that guides. Others create a universe that collapses. But beneath all these differences, one idea glows softly. the idea that quantum mechanics is still incomplete in its meaning, even though it is complete in its predictions. We can describe how particles evolve, how waves interfere, how probabilities behave, but we do not yet know how to interpret the equations in a single, universally agreed-upon way. The mathematics is solid, beautiful, precise. The meaning is open, subtle, and deeply mysterious. And as this mystery unfolds, another recognition rises gently. The interpretations that involve observers, or consciousness, or information are not fringe ideas. They were developed by the founders of quantum mechanics themselves, by Bohr, von Neumann, Wigner, Heisenberg. They were refined by modern physicists and philosophers seeking to understand what the equations are truly telling us and what they are not. And even interpretations that do not involve consciousness still must grapple with the role of information, with the concept of measurement, with the fact that quantum systems behave differently when they interact with macroscopic apparatus, or with the environment, or with observers. No interpretation escapes the observer entirely. Each one must answer how measurement becomes a definite outcome, how potential becomes actual, how the gentle, shimmering wave of possibilities becomes the single experience of the world we encounter in awareness. This is why the question lingers, softly, endlessly. Does consciousness create reality, or does reality create consciousness? Or do they arise together, interwoven, each shaping the other in ways we do not yet understand? The interpretations that involve observers do not settle the question, but they illuminate it, like lanterns placed at different angles around the same enigma. They show us that the observer cannot be removed from the story of quantum mechanics, not entirely, not cleanly, and that the meaning of that connection is still open to exploration. They show us that consciousness may not force outcomes, may not collapse waves, yet it stands at the end of every measurement, receiving the information that makes the world appear definite. They remind us that reality is both mathematical and experiential, both external and internal, both independent and relational. And in this recognition, a quiet truth emerges. The universe is not merely observed, it is participated in, observed from within, understood from within, experienced from within. And as these ideas settle gently, like dust drifting in a beam of soft light, the mind becomes ready to explore the next layer of the mystery, a deeper question, a more intimate puzzle, the question of whether consciousness might shape reality itself. The idea that interpretations of quantum mechanics can differ not only in mathematical structure, but in their treatment of observers, creates a landscape almost as strange as the quantum world itself. A landscape where the same equations describe the same universe, yet the meanings, the metaphysics, the deep story of what is real shift from one interpretation to another. And in this quiet space, we continue unfolding the remaining ideas of this section, slowly, softly, until each one is complete. One of the most striking contrasts in this landscape appears when we bring many worlds into the gentle light, a theory that removes collapse entirely, a theory where nothing chooses an outcome, a theory where every possibility continues to exist, and where our experience is only one thread in an unimaginably vast branching structure. This interpretation, unlike Wigner's proposal or von Neumann's chain, does not rely on consciousness in any way. It does not grant the observer a special role. It places the observer inside the universe, as just another quantum system, evolving unbroken, without mystery, without discontinuity. And in this view, the entire debate over consciousness causing collapse becomes unnecessary, because collapse itself in many worlds does not happen. But the calm simplicity of many worlds rests on a deeper and more subtle idea that what looks like collapse, what looks like a sudden jump from many possibilities to one, is actually the smooth unfolding of the universal wave function, where decoherence, like a quiet, diffusing fog, makes branches separate and makes interference between them vanish, not because something has chosen, but because the environment itself gently absorbs the coherence, leaving each branch unaware of the others, like ships drifting apart across a silent, fog-covered ocean. Each one real to those aboard it, each one inaccessible to the others, and in that distance the illusion of collapse is born. Many worlds leaves consciousness untouched, unaffected, unnecessary as a mechanism, Instead of consciousness choosing a reality, reality simply contains all outcomes, and consciousness becomes the process of following one path through the branching structure, a path shaped by decoherence, by probability, by the structure of the wave function itself, nothing more and nothing less. But this view, as serene as it appears, raises its own questions. If all outcomes exist, what makes the world feel singular? If every possibility unfolds, why do we only remember one? And deeper still, if consciousness is only a passenger within one branch, then what is the meaning of choice? What is the meaning of probability? Why does the universe feel like it has a story at all, when in many worlds every story is told? And yet, despite its implications, many worlds remains a cornerstone interpretation, not because it is easy, but because it removes the need for special observers, special moments, special collapses. It replaces discontinuity with continuity, mystery with mathematics, and the fragile idea of a conscious observer influencing outcomes, with the quiet, continuous unfolding of a universal wave. But not all interpretations embrace such abundance. Some instead offer the opposite vision. A universe that does not branch endlessly, but collapses physically, objectively. No consciousness required, no observer needed, only the world itself choosing outcomes. Quietly, reliably, through mechanisms not yet fully understood. These are the objective collapse theories, proposals that seek to place collapse inside nature itself, not as a mental event, not as an update of information, but as a physical process, something built into the universe, like a whisper in the fabric of reality, a soft tendency for large objects or complex systems to fall into definite states, slowly, inevitably, as if coherence cannot survive beyond a certain scale, as if nature prefers definiteness, prefers clarity, prefers the quiet stillness of a single outcome over the shimmering ambiguity of superposition. Among these theories, the most well-known are GRW-type proposals, the Girardi-Rimini-Weber model, which suggests that every particle has a tiny probability of collapsing spontaneously, a probability so small it barely affects a single atom, but becomes overwhelming in large systems, causing definite outcomes to emerge naturally, without needing an observer, without needing consciousness at all. Collapse happens because nature collapses, because the universe does not allow superpositions to survive at macroscopic scales, not because an observer appears. Another objective collapse idea ties collapse to gravity itself, suggesting that mass, or space-time curvature, may dislike sustaining superpositions of large-scale structures, that perhaps superpositions strain the fabric of space-time, and collapse resolves that tension, putting the universe back into a stable configuration, like water settling into a still surface after a small stone disturbs it, quietly, automatically, without any mind involved. These theories, unlike many worlds, keep a single reality, but they also remove consciousness from the equation. They shift collapse from the realm of knowledge into the realm of physics, a real event, a real process, a real choice, made not by a mind but by the world itself. And this brings us to another subtle and deeply important contrast. Interpretations that emphasize information, not consciousness, not collapse as a physical event, but the idea that measurement is fundamentally about information exchange, not between mind and matter, but between systems. This brings us back softly into the realm of relational quantum mechanics, but also into the broader idea that facts, outcomes, and states may be relative to the observer only in an informational sense, not dependent on consciousness, but dependent on the relations between systems. In this perspective, the universe is not a place where properties exist in isolation or where outcomes exist independently of who examines them. Instead, properties exist only in relation to something else, a system they interact with, a context, and consciousness, once again, is not required. But this information-centered view opens a doorway to another interpretation, one that is gentle, subjective, yet deeply rooted in Bayesian reasoning, a view called cubism, quiet, personal, and very different from the others. Cubism does not say that consciousness collapses the wave function. Instead, it says the wave function does not describe the world at all. It describes the observer's beliefs about the world, not the universe's state, but the observer's expectations, their probabilities, their subjective degrees of belief. In this view, measurement outcomes are personal experiences, the way the world responds to an observer's actions, not because consciousness changes reality, but because the wave function is never a property of reality in the first place. It is a tool for making predictions, a tool that belongs to the observer. This interpretation does not give consciousness magical powers, nor does it make reality depend on the mind. Instead, it redefines the role of the wave function entirely. It becomes a guide, a map, a personal interface for predicting future experiences. And collapse becomes something like updating a belief, not changing the world, but refining expectations, quietly, internally, in the mind of the agent using the theory. And in this gentle, introspective view, the universe itself remains untouched. Only the observer's knowledge changes, only their internal model adjusts, and consciousness, while present, is not a cause of collapse. It is simply the seat of belief, the place where probabilities live. And so, across these interpretations, we see a wide spectrum. Some give consciousness no special role at all. Some give it a foundational place. Some treat collapse as subjective. Some treat collapse as physical. Some remove collapse entirely. But only a few, a very small few, give consciousness the power to create outcomes. And even in those cases, it is not a scientific claim, but a philosophical extension, a question, a possibility, an interpretation, not an established fact. In the quiet of this long unfolding, it becomes clear that the debate over consciousness in quantum mechanics is not a scientific battle between right and wrong, but a philosophical conversation about what the mathematics means, a conversation still open, still unresolved, still beautifully mysterious. There is a moment, quiet as a drifting thought, when all the ideas we've explored begin to lean toward one another, quantum mechanics on one side, consciousness on the other, and between them, a question that glows softly in the dark. Does consciousness create reality, or does it simply witness it? Or is the truth something deeper, far more subtle, woven into the structure of the universe itself? Tonight, we move gently into that space where science meets philosophy, where equations meet awareness, and where the boundaries of what we know begin to dissolve into something open and beautifully uncertain. To begin, we let the scientific frame settle quietly around us. In physics, the line between what is known and what is possible is always shifting. Wave functions, measurements, observers, superpositions, all of these ideas carry clear mathematical meaning. But consciousness, awareness itself, the lived experience of observing, that is something the equations do not explicitly describe. And yet, the equations leave room for mysteries, not because they are incomplete, but because they point towards something we do not yet fully understand. Something about the relationship between information and reality. Something about the way possibilities narrow when interactions occur. Something about the strange silence inside every quantum system until something touches it. Something about the thin place where probabilities become facts. So we begin here. With the first piece, this section must explore the scientific boundaries, the places where physics says this we know and this we do not know, and this is not yet answerable. Boundaries are not barriers. They are gentle invitations to rest in the truth of what is understood and the beauty of what is still unknown. Quantum mechanics, as it is practiced by physicists every day, does not require consciousness to make reality behave. The experiments work whether a human is looking or not. Things decohere, systems collapse, interactions select outcomes. The moon does not disappear when no one is watching. Electrons do not drift into ambiguity when the lab lights are turned off. And yet the theories remain strangely open in a way that allows room for deeper questions. Because even if consciousness does not cause collapse, even if the observer is not needed to crystallize reality, there is still a profound puzzle. Why do definite outcomes exist at all? Why is there a single thread of experience flowing through a universe built from possibilities? Why does the wave function, mathematically perfect, endlessly unfolding, ever give way to the moment when something becomes real? The equations make predictions, but they do not explain the metaphysics. They do not explain why our experience of reality is so precise, so crisp, so undeniably definite. Why this moment and not another? Why this outcome and not the field of alternatives? This is the gentle edge where science meets philosophy. And here is where the second piece emerges. The philosophical possibilities, Not the wild assertions, not the exaggerated claims, but the genuine, careful, tentative ideas that physicists and philosophers have studied quietly for decades. Possibilities that ask, is the universe participatory, as John Wheeler suggested? Is information more fundamental than matter? Is the act of measurement an act of drawing distinctions, drawing boundaries between what is and what could be? Could consciousness be related to the very act of distinction-making? Could the universe be structured such that awareness is not an accidental byproduct, but a natural outcome? Perhaps even a necessary ingredient? We do not know, but the question is not unreasonable. It is vast and quiet and open. It is the kind of question that does not demand an answer, but invites contemplation, like a distant star whose light reaches us long after the moment it was born. Then the third piece enters, softly. Wheeler's idea of a participatory universe, an idea he did not mean romantically or mystically, but scientifically. Wheeler imagined a cosmos in which observers do not merely record data. Observers, through interactions, contribute to the unfolding of reality. Not because consciousness bends the universe, but because information itself may be woven into the structure of existence. Like threads in a cosmic tapestry, the observer, in Wheeler's view, is part of the universe's self-questioning process. A participatory loop. The universe asks questions by evolving possibilities, and observers answer through interactions that select outcomes. The universe responds, adapts, evolves, and the cycle continues. This does not require consciousness to be magical or fundamental, but it suggests that observers, whatever they are, play a role in how the universe becomes definite. Not because they intend to, but because any physical system that interacts makes distinctions. And distinctions are the teeth of information. From here, the next idea reveals itself slowly. The nature of information. Perhaps matter is not the foundation. Perhaps energy is not the foundation. Perhaps the deepest layer of the universe is something like information, the patterns, the relations, the distinctions, the ways in which systems differ. The universe may be built from difference, from structure, from contrast, and consciousness, in a soft and humble sense, may be the experience of traversing those structures. Awareness may be the feeling of moving through information, interpreting, compressing, making meaning. Not because consciousness shapes reality, but because consciousness is one of the universe's ways of reading itself, one of the universe's ways of perceiving its own possibilities. The next idea unfolds naturally. Could consciousness be emergent? A phenomenon rising from countless interactions between particles and fields, a pattern born from complexity, like weather emerging from the atmosphere or music emerging from vibrating air. If consciousness is emergent, then it does not create reality, but it interprets it, it reveals it, it gives it form within experience, it transforms raw data into meaning. This is a gentle, grounded view, a scientific view, but not the only one. Another possibility whispers, could consciousness be fundamental, not emergent, but elemental, like space, time, energy? Could consciousness be a basic aspect of the universe, not in a mystical way, but in a physical sense, like a field? A field that integrates information, interprets structure, experiences unfolding patterns. We have no evidence, no experiments that require this idea, but we cannot rule it out. The universe leaves the question open. And then, a third possibility, consciousness as an interface. A surface, a translation layer, between the biological brain and the quantum world. A way for organisms to read the probabilistic universe as definite experience. Like a dashboard hiding the deep machinery. The brain may not show us reality, but a useful, coherent version of it. Not because reality depends on us, but because reality is too vast, too complex to be perceived directly. The interface shapes experience, not existence. And so we reach the final idea that must be discussed. Science has not yet found proof that consciousness creates reality. Wave functions collapse without human minds. Particles decohere in the dark. The universe was here long before life emerged. Yet the question remains open, not because of evidence, but because of wonder. Because the mathematical structure of quantum mechanics leaves room for interpretations, room for possibilities, room for quiet mysteries. And sometimes, a question is beautiful not because we can answer it, but because it stretches our understanding toward new horizons, because it reminds us that the universe is not small, not finished, not fully known, because it invites us to breathe more slowly, to rest in the uncertainty, to let curiosity drift gently like a feather in a still room. The truth may be simple or subtle or far beyond the limits of our current science. But tonight, in this quiet moment, it is enough to listen to the mystery, to feel the soft glow of possibility, to drift into it like a dream. Let the question remain open like a window onto the unknown. Let the universe be what it has always been, vast and silent and full of gentle secrets. Let everything grow quiet now. Let the thoughts that were moving quickly slow down and drift, like small particles settling through a still pool. You've wandered through quantum states, through superpositions, through the strange and subtle edges where physics brushes against philosophy, and now you are arriving at a softer place, a place where the mind can unclench, where the universe no longer needs to be solved, and where the beauty of not knowing becomes its own kind of comfort. The night around you feels wider now, as if the air itself has made room for all the unanswered questions. Questions about consciousness, questions about reality, questions about what it means to witness a universe that is always unfolding, always becoming, always shimmering between what is known and what can only be felt in the quiet of the mind. There is something deeply peaceful about this boundary, this threshold between certainty and mystery. Because for all the equations, all the experiments, all the interpretations and debates, there remains a simple truth. We do not yet understand what consciousness truly is, or why the universe appears to respond so delicately to the act of observation. And instead of seeing that as a failure, you can let it feel like opening a window into possibility, into wonder, into the sense that reality might be far more layered, far more intricate, far more softly intelligent than we imagined as children or even as adults. Some mysteries are not meant to be closed tightly, not meant to be labeled and filed away. Some mysteries are invitations to breathe a little slower, to rest a little deeper, to see the world not as a solved puzzle, but as a living question. A question that gently surrounds you, with every heartbeat, every thought, every drifting moment. As you lie here or sit here, with your eyes growing heavier, you can imagine the universe not as a cold mechanism, but as a quiet sea of possibilities. A sea where particles shimmer between states, not yet choosing, not yet defined, like thoughts before they form, like dreams before they take shape. A sea where consciousness doesn't have to force anything, but simply floats, aware, curious, open. There is a gentle kindness in letting go of the need for final answers. Because the universe has been unfolding for billions of years, and it will continue to unfold long after every theory today has been rewritten, refined, or replaced by something utterly unexpected. And here you are, a conscious being, briefly awake within that vastness, a momentary flicker of awareness, inside a cosmos that may itself be dreaming. Let yourself drift with that thought, softly, not clinging to it, not analyzing it, just floating alongside it, like a leaf on a slow-moving river, until the river carries you into deeper calm. The beauty of the unknown is that it frees you. It frees you from having to control everything, from having to understand everything, from having to hold every idea in your hands at once. You can place the weight down now. You can loosen your grip. You can give yourself permission to be small, to be curious, to be quietly astonished. Because somewhere in the spaces between atoms, in the hush between quantum transitions, in the silence after an observation is made, there is room for wonder, there is room for rest, there is room for dreams. Every question you explored tonight still remains open, but it no longer needs to feel sharp or urgent. It can simply be an open door, leading into a quiet hallway, lit only by soft, ambient starlight, the kind of hallway where you move slowly, gently, letting each step carry you deeper into peace. And as you move through that softness, you might notice the subtle truth that has been present the whole time. Consciousness, your consciousness, is not something separate from the universe. It is part of it, an expression of the same laws, the same patterns, the same deep logic that govern the motion of galaxies and the trembling of electrons. You are not outside the cosmos, trying to peer in. You are within it, made of it, a temporary constellation of matter and awareness, a brief alignment of atoms, remembering itself, wondering about itself, and that alone is extraordinary. Let that thought warm you. Like a soft ember in the chest, let it glow and brighten, and then settle into a steady radiance. not demanding anything, not requiring explanation, just a simple brightness, a quiet presence, a reminder that existing at all is its own kind of miracle. As your breath slows, as your mind unwinds, you may feel the edges of the world blur a little, thoughts softening, sensations drifting, awareness becoming lighter, as if gravity itself were easing its hold. This is the moment where wakefulness dissolves, not suddenly, but gently, like ink fading into water. Each ellipse, each pause, each space between words becomes a stepping stone, leading you further from the noise of the day and deeper into the quiet that waits beneath it. You don't have to think now, or analyze, or hold on to any of the ideas you've heard. They can all drift away, floating upward, like dust in a sunbeam, until only stillness remains. Stillness in the body, stillness in the breath, stillness in the long, slow rhythm of the universe, moving around you and within you. If consciousness creates anything, let it create rest, let it create calm, let it create the soft inner space where nothing must be decided, nothing must be proven, and nothing must be feared. Only presence, only quiet, only the gentle unfolding of experience, moment by moment, breath by breath. You can imagine yourself drifting now, as if carried through the depths of a cosmic ocean, a warm, dark ocean, filled with the quiet hum of quantum fields, where every ripple is small, every vibration gentle, every movement slow. Nothing rushes in this ocean, nothing competes, nothing struggles. It simply exists in a state of calm becoming, and you, floating in its depths, are part of that becoming, part of the mystery, part of the unfolding, part of the quiet intelligence that permeates the whole of existence. Let the boundaries soften now, between thought and dream, between self and universe, between what is known and what is beautifully, peacefully unknown. Let the last awake part of your mind melt into something quieter, something slower, something softer, a gentle descent into a state beneath words, beneath questions, beneath the need to understand, a descent into rest, into stillness, into the quiet mystery that holds you, always. And now, as all of this settles, as the night folds around you, and your awareness grows lighter, and the boundaries between thought and dream blur, I'll leave you with one last soft idea, a small, weightless truth to carry you into sleep. The universe is not something separate from you. You are a way it looks at itself, a way it feels itself, a way it briefly becomes conscious of its own unfolding, and even when you sleep, you remain part of that unfolding, drifting, resting, held gently within the quiet depths of the cosmic mystery. Sleep well, and drift softly through the unanswered questions and the stillness that waits beneath them.